Hi, everyone. I'm going to be talking about my final exam submission, just walk through the code and a quick discussion of everything that was needed. So the first problem is talking about three different probability densities, essentially a gamma, a sum of exponentials, which actually indirectly is a gamma, and then an exponential probability distribution function. And so in R, it's fairly easy to do all of these things, basically setting a lambda, an alpha, and the number of values that you want in your hypothetical distribution data set. So we've done that here. And so I think what the main purpose of problem one is, at least between 1A and 1B, is to demonstrate that you can use many different methods to calculate the mean and the variance, and that the calculus approximation is essentially the true empirical mean or variance / standard deviation that you'd get. So, I mean, we kind of run the mean and the variance here, looking at what the values are for the different distributions. And although I did research and learn a little bit more about the sum of exponential distributions and how that pretty closely correlates with a gamma distribution, we can see that a lot of the values, even for random selection, have a similar mean and a fairly similar variance. And then as we explore kind of the calculus proofs in 1B, so essentially the premise of taking an integral for the gamma proof from kind of reviewing and learning a little bit more about it as part of the final exam is that to take an integral typically of a gamma distribution, you'd like to essentially modify it or simplify the term so that you have it itself, and you can simplify to a constant in terms of what you pulled out with the math here. But that's basically what I learned in terms of kind of working with proofs related to gamma distributions. But you'll see that when you get to, I guess, what a math textbook would tell you is the mean of a gamma distribution, alpha over lambda, you see that that approximation is incredibly close to just taking the mean of the distribution overall of a random sample. So in terms of the variance, it's the same type of concept. It's mostly simplification of your integral. Basically the variance using the simplified formula to calculate the variance. And what you're really doing is trying to simplify the term so that you have basically a gamma distribution with some variation of your alpha and your beta, in this case lambda. So it's just simplifying the terms to get alpha plus 2 and then ultimately lambda as well. And as you simplify your function, or not your function, but your integration steps, you're able to say that because you know that the PDF or a valid PDF of a given function has to sum to 1, you simplify your integral to be 1, leaving you with just constant terms to simplify to that point, and that gets you to this value here. And consistent with the mean, you have a very similar value for your approximation for variance using the, I guess what you'd call a more theoretical mathematical approach. And so a similar process to kind of use the moment generating function for exponentials, calculate the expected value of the single exponential and the sum of exponentials. So we look to calculate the moment generation function, which essentially creates what's the expected value. So you see here for the exponential, we create the integral. We start to simplify by moving lambda out. And then we take integration actually, and because it's, I guess a t value of 0, or I guess a moment generating function at 0. So then we take the derivative, and that's the ultimate result of our or what the potential value would be at that moment. So then when you plug in 0 for t, and you apply the lambda value, you get 0.1667, which again, like I kind of mentioned before, gives you a very close approximation. So it's just interesting to kind of give insight into different ways of calculating, or again, more of a proof of why the math does work, in fact. And so, because in this case, the sum of exponentials, basically it's the same process as the exponentials. You just take whatever the number of sums that, or I guess the number of exponential distributions that you added together, and that's how you calculate the, I guess, the preliminary moment generating function. You take the derivative of that function and you're left with this. And then when you plug in 0 for t for the first moment, you get that value, which again is similar to all the others. So now moving on to 1C through E. The premise, I think, of this is basically to demonstrate mathematically that the memoryless property holds. So we're given 3 different prompts, basically to calculate what is the conditional probability for an exponential distribution given different values of lambda. So we just gave a proof here in terms of simplifying the conditional probability for that. And ultimately we're left with e to the lambda over whatever the actual constant term that's applied to lambda minus the initial term, and then divided by the conditional term. So once we kind of step through that process, I wasn't entirely sure about what you meant for the calculus for memory properties, so I just applied what the CDF was to show that those matched across the different examples that you gave for the conditional probability. Okay, so the next step is talking about loosely investigating the marginal and joint probabilities based off of quartiles for the two distributions when you multiply them together. So what I did here was I took the quantiles at 4 key, I guess, the standard quantiles, and then I did matrix multiplication to actually combine them to see what the joint probabilities are. And I think the premise around this process was essentially to determine that you could combine the probabilities and then make sure that you didn't have to account mathematically for taking out pieces where they're dependent. I guess the distributions were dependent, which changes the conditional mathematical formula. So basically what I did to create the table was then I said I summed up the total column and total row values. And once I did that, I divided that by each row value. So that way I could get it inherently like a percentage for each quadrant to be able to determine that those were, I guess, the sub percentages across that full quadrant. And then I did a little bit of validation to make sure that the sums for rows and the sums for columns actually all agreed. And so then you would ask to see if independence using Fisher's exact test and the chi-square test held, and then kind of a quick explanation of what the two are. And so essentially what these two tests are meant to do is to test typically categorical data in terms of categories to make sure that they're independent. But you can use the chi-square test to test for independence, I guess, across distributions as well. And that's why I think it's a more appropriate test in this case. So when running those two tests, we kind of get the output for what the p-values and the statistics are. And so we see a very high p-values, and I guess there is a warning related to this, and I think part of it is that it's looking for standard counts typically, and I think that's kind of a question maybe that's left that I need to research for non, I guess, integer-based distributions. Like, is there another way that I should have been modifying the test itself to be able to confirm that's correct? Because I got p-values of 1 for all of these tests for the different distributions, and I basically transformed it a little bit. So because it was talking about 2 columns, I ended up transforming it as 2 columns as well for the initial quantiles to see if that changed the test. But ultimately, I still was getting very high p-values using Fisher's test and chi-square test. But reading a little bit more about Fisher's exact test, it was initially designed for 2x2 matrices. That's why I thought it was a little bit less appropriate. And then some resources I read through talked about how it can be very computationally expensive for larger matrices. So that's why I think the the chi-square test is more appropriate. And then moving on to the housing price predictions, we're loading in the trained data set and just kind of looking through the different columns here. And there's a lot of columns. I think there are about 70 something that were available for the data set. And initially, to kind of go through the review of it, I needed to look at the summaries of different columns. I also they had some documentation available on the website to kind of talk through what each column was. And I think given that there were a lot less continuous numerical variables, it was definitely helpful to have that documentation because you needed to know what each description kind of corresponded to. There were a lot of character variables. And I tried to do some feature engineering to be able to add value to the model and predictive, I guess, capability. So we don't need to scan through all these fields, but that's basically a quick summary of them. And then I just tried to visualize some of the relationships overall, kind of looking at distributions for bedrooms above ground, looking at bathroom distributions for full bathrooms. I looked at the year it was built, kind of looking at that distribution because I thought age would be a factor. And then kind of plotting the relationship between bedrooms above ground and sales price. And obviously, since this is a discrete variable, that changes it a little bit, but you see the shape here overall is not so clearly linear. And then we see that the ground floor living area square footage does have some type of linear relationship between that and sales price, but we see some fanning out overall. It's not necessarily, so that might be a concern in terms of including it in the model. We looked at overall quality, which is something I think was maybe it was a discrete variable, but it kind of already was configured. And I thought it might be a good metric. And there is a linear relationship here between that and sales price. So ultimately it was included in the model. And then I was just looking at some of the other miscellaneous types of character variables to kind of understand like how present they were, and then how, I guess, look at the frequencies overall of some of these other things that might impact. Like I know personally that if you have a pool that's in bad shape, that actually can substantially impact the price. And so that's why I was looking at pool quality over here. And then there were some miscellaneous features. So I was curious like how common they were in terms of the data set, and overall most of them were null. And so I kind of looked at across the board to try and assess which variables maybe I could one hot encode and piecemeal to kind of determine if it was potentially useful. So for example, new households or a standard, I think this is close I'm not sure exactly what COD stands for off the top of my head, but I think I have a definition for it later on. And then I just kind of slightly mutated it to age instead of the year built, so that it was again, it is very similar, but to kind of look through the distribution in a way that is, I guess, a more numeric variable. And we see, I mean, I did put a G on smooth by itself, and I didn't set the parameter in terms of using linear, so it looks like the standard one is slightly quadratic. And I explored using that as an interaction term, or not an interaction term, but like modifying it in terms of a model to see if that would impact it by squaring it. And then you had asked for correlation. Let's see. So yeah, you wanted, or we needed to look at 3 different quantitative variables and then test correlations to see if there was a 0 relationship, essentially that there's somewhat of a linear relationship. So I kind of looked through the data set and was trying to find continuous variables. I decided ultimately to include one non-continuous one in terms of the, I guess, a discrete variable in bedrooms above ground. But I just quickly plotted the relationships between the 3 to kind of look at the patterns overall. And there's not a very strong linear relationship between age and first floor square footage. There isn't necessarily such a strong pattern. When we're looking at the discrete variables between age and bedroom above ground, also not a incredibly strong relationship. Same with, so basically any of the relationships between the above ground bedrooms is not so strong, and that comes out in terms of the correlation itself when we're looking at what the values are in terms of the confidence interval. So we did the pairwise across the 3 different permutations. And so when we do the 80% confidence level, we see that there's a slightly negative relationship. And I think age and first floor square footage have the strongest correlation of all of the pairwise correlations, but we see that 0 is not included. And then when we do age versus bedrooms above ground, a slightly weaker correlation, but overall does not include 0. So we look at the last one here, and we also see that there is some correlation, but not as strong as the first comparison. And so because each one, given that the p-value is very, very small, even though we're doing 80% confidence interval test, and also the fact that 0 is not in any of these confidence intervals, we failed to reject the null hypothesis, which in this case is the correlation is not 0. And so it's fair to say that these items have some type of linear correlation or linear relationship overall. It's kind of what's quick summary of what's being explained here in this paragraph. And then to take it a step further, we were inverting our matrix into a precision matrix and then multiplying that by the correlation. So multiplying the correlation by the precision by the correlation, and then decomposing it. So we basically combined correlation times precision times correlation to create a new matrix in terms of, and again, we have the identity kind of on the diagonal here, and then quickly running the LU decomposition. Again, it was much easier when we had the pre-built function. But running that, we were able to kind of look at the lower and upper matrices to see what they were. And then kind of moving on to the next part of the problem with the final exam was modifying a right skewed data set, and then basically running a I guess, a transformer to turn it into an exponential probability distribution function. And so I looked at 3 different ones: open porch square footage, garage area, wood deck square footage, ultimately decided an open porch square footage. We see this is mostly present with 0, and then a pretty heavy right skew. And we'll talk further about why some of the 5th and 95th percentiles, I guess, had the values that they did. So I was just quickly checking if whether or not the values were NA or 0, but the vast majority are 0. And then running that mass fit distribution data set on the specific field. We want to fit it to an exponential. So the lambda rate, in order to get it as an exponential, is this value. And then we did repeated samples of that, using that estimate to transform 1,000 data points. And when we plot the distributions together in terms of histograms, we see overall the shape is not so different. I think the biggest piece of, or the biggest change from the exponential is the fact that it's a much smaller skew, and that makes sense because as the exponential spans out across the x-axis, it's meant to have a lot less likelihood. And so it basically pulled in the values here towards the left. And I think that was the premise in terms of what happened really with the transformation. So when we look kind of at the percentiles overall, we are using kind of the standard R function for quantile exponential, using the lambda rate, and we're putting basically what's the percentile to get the value that we want. And we're calculating using a t statistic to try and measure what the mean, and getting a 95% confidence interval of what we think the mean value is for those percentiles, or the percentile values. And then lastly, we're just running kind of a quick standard, what was the quantile of the original data set. And so these 3 methods are kind of all very similar overall. I think the key thing to note is, since the data heavily skews to 0, since a lot of houses don't have porches or open porches, we see that there is a 0 in the confidence interval, so it very much could be 0, and that makes sense given that the vast majority of data is 0 value on the original data set. Whereas when we kind of transform it to exponential, it shifts it a little bit, but inherently it's not that far from 0 either. And then I guess in terms of comparing the differences between the 95th percentiles, between what the exponential showed and what the quantile showed of the original data point, is consistent with reviewing the distributions, in that the skew is substantially diminished once we transformed it. And that's leading to the discrepancy across those 95 percentile values. And so moving on to the multiple linear regression analysis, kind of using most of the visual analysis and review that was done before. We basically had tried to come up with some feature engineering for variables to determine whether or not they might be useful or not. So most of it was one-hot encoding, depending on whether the value was provided or not. And so we created a bunch of different one-hot encoding variables. So for example, trying to see whether or not the property had central air, or whether or not it was unfinished, whether or not it had a porch, whether or not it was closed. So COD meant closed by a court officer, whether or not it was new. And again, there is a risk, I guess, there that it could be very highly correlated to age. And then looking to see whether or not the house itself was classified as functional or not, or there were deductions, basically were there, I guess, deficiencies within the house itself, and then assessing the kitchen quality overall, kind of adding a numeric value for that. So when we first ran this initial multilinear regression model, we see that basically all the variables included here are significant. And I did do a little bit of backward testing myself to kind of eliminate some of the variables. So I eliminated the house unfinished because that wasn't significant. And I eliminated, I believe, has porch, because that wasn't significant. So there was a little bit of backward testing here to kind of look through and identify which variables might be significant. And when looking at the model summary, the initial concern for me was that the residuals were not so closely averaging around 0, and it was actually a much lower level for the negative. The interquartile range doesn't seem that far off, I guess, in terms of assessing that there's not necessarily a distribution. We can look at diagnostic plots, but min max are a little bit off. So maybe there's a slight skew to the data overall, but the main concern is that it's not 0. And then from looking at the first, I guess, the F statistic, we have a very small p-value. So we know that the model itself has some significance. The adjusted R squared, given that we have a bunch of variables, is not dramatically lower than the R squared itself. So the penalty function is not that substantial. And then, like I said, we kept everything that was included as a significance of less than 0.05 here. And so what I did realize actually is I hadn't kind of visually looked at all of the variables that are included in the model here. So I just had quickly tried to use KDE pairs to review and confirm that items, like I guess the relationship across different items overall, and nothing really jumped out so high in terms of correlation, but I decided, let me just run a variance inflation factor test. And what we notice is that there's one value, the ground floor living square footage area, has a value of 7.48. I know we talked about in class that anything over 5 is really has a strong concern of multicollinearity. I know you had said 3, but I was thinking if I pulled that out, how would that impact second floor square footage? And it kind of makes sense if you represent, okay, what's the bedrooms and bathrooms, it should probably correlate to square footage overall. And so what I decided to do was exclude ground floor square footage and rerun the model. And so we rerun the model, taking out that item, and we notice, hey, maybe that multicollinearity was throwing off the coefficients and the p-values for a bunch of predictors, or I guess independent variables that we had. It didn't dramatically reduce the adjusted R squared. It was about 3% of the variability was no longer predicted within the model. And so now we needed to kind of further test that. So we took out basically all of those p-values that were insignificant, and to see what the impact of the model was. And we actually get very minimal diminishment of our adjusted R squared. Our F statistic is still very small. And I guess the remaining concerning item, kind of just looking at the summary, is that the median of the residuals is still not that close to 0. Overall, min-max and the quartiles haven't changed that dramatically from the first iteration of the model. And when we look at the diagnostic plots, there isn't necessarily such a strong clear pattern in the fitted residuals diagnostic plot. However, there is showing here with this red line that's kind of pre-built in the R, a slight relationship or pattern that I guess could be visible. And there are some higher outliers here that could impact the model overall. And that's, I guess, consistent with the normal QQ plot in terms of, it seems like it's very good approximation for the, I guess, the 2 quantiles. So probably most of the data. And as you get to the end, to the third quantiles, pretty heavy skew, more so on the right, that might violate the assumption overall in using this model. So those are, I guess, the main concerns around assumptions related to linear regression with this data set. And then rerunning the variance inflation factor, we see that everything is now below 3, which I think is a good thing. So that wouldn't disqualify the model. So then bringing in the test data set and just running some of the basic feature engineering on that test data set to make sure we use that, because some of the variables that were created are included in the model. So running the prediction on the data set. And then I was just making sure, because I didn't necessarily account for nulls as much in terms of the initial review. So I was just testing to see what null values existed in the test data set. And then most of it is just the end cleanup for submission, because the request only wanted ID and sale price name, and those labels basically had to be named. But that's essentially the talking through the full final exam, and I'll include a screenshot in my submission within Blackboard.